Okay, off we go. So, sorry for the late start. Here we go. So, last time we were talking about linear approximations. And, let me get a little light here. So remember the big idea of a linear approximation is we're trying to mimic the function. Right? So the function has, for example, in single variable, there's a certain value and a certain derivative that f has at a given input point a, and we're going to look for the degree 1 polynomial that has the same value and the same derivative. It's copycatting f best it can with a degree 1 polynomial. Okay. All right. So we talked about how to generalize this in a multivariable setting. So in particular, now look, we're going to have multiple input variables. Now, quick aside, still only one output variable. We'll talk about multiple outputs in just a second. But with multiple input variables, how do we accomplish the same thing? Namely, we've got a function that has a certain value and certain partial derivatives at the point in question. How would we copycat that? How would we find a degree 1 polynomial called L that has the same value and all of the same partial derivatives? Right? So again, that's our best we can do to copycat f at the point A. Okay. And what we talked about last time is that this is the function that does it right there. And this is a good exercise. You can check that for yourself. And I think it's a good exercise to do that. Right? And just keep in mind in that process that as much as this looks like a complicated thing, and likewise this, and likewise all of the others, analogous factors at the other terms in the ... in between, those factors look complicated. They are constants, right? Because while partial derivatives are functions, this line says, yeah, but evaluated at that fixed given constant input point A. And so this then just becomes some number. So treat it like a constant when you're taking derivatives because it is literally a constant. Okay, right. So, make sure to check that this does as claimed. And that's where we left off last time. Now, what I want to do is I want to look at this part of the function, right? So, there's also the f of a. That's, of course, got to be there, but let's just not pay attention to that for just a quick moment. Let's look at this part here, and let me make the observation that there's a bunch of factors that all kind of look the same. They're all partial derivatives. And then the other factors in each term also all kind of look the same. And in fact, what you notice pretty quickly, let's see, let me get into the right mode here. What you notice pretty quickly is that all of those factors in blue are just literally the coordinates of the x minus a vector. How about that? What are the odds? Okay, well, cool. That worked out nicely. Having made that observation, now I see that I have a sum of products. Where have I heard that phrase before? Sum of product. Oh my gosh, that sounds like a dot product, doesn't it? I have a sum of products, and furthermore, one of the, if I were going to view this as a dot product, I would sort of have to view what I have in blue here as being a vector. And it is a vector. I don't have to take some weird point of view to choose to view this as a vector. It already was. X minus a. X is some point in the domain. A is some point in the domain. X minus a just represents that displacement between the point where you're doing the approximation and the point where you're evaluating the approximation. Well, this strongly suggests that I could choose to rewrite all of that, what I have in purple, literally as a dot product. This other, all this stuff in green, I don't really recognize, but I can just say, hey, all that stuff in green, let's call that this thing. It's called the gradient vector. It's a weird choice. to say I'm going to be interested in this vector whose coordinates are the various partial derivatives of my function. But, I mean, look how nice, right? I mean, it takes this big, long expression that has a dot, dot, dot in it, and it rewrites it as a very compact, nothing but a dot product. And I'm going to say a natural dot product in the sense that it's a dot product with a vector that we were already interested in. X minus A makes sense. That's right there in our picture. Right? Again, displacement. So for the moment, this is a notational choice, calling the gradient calling this a vector defined by this formula. It's just for notational purposes, so that I can rewrite this ugliness as this much nicer, more compact thing. We are eventually going to notice that while we motivated this by notational convenience, it's actually a really natural thing itself. But that's not something we're ready to talk about yet. Anyway, this is the new version, sort of the new way of writing the same formula. So again, here was our linear approximation. This is the unique polynomial that has all the nice features that we want it to. And here's a different, more compact way to write it. And frankly, really just a better way to write it. So heads up for this notational choice. Okay, and then before I go on, let me make another observation I think is really cool. Let's compare now our single variable linear approximation and our multivariable linear approximation. Let's see here. They both have f of a. They both have a second term. And in that second term, I am in each case multiplying by x minus a. Oh my gosh, the analogy is so strong, right? Like, wow, it's like the exact same thing in some sense. And continuing that analogy, how should I think about this dot product with the gradient? Well, we seem to have a suggestion here that dot product with the gradient it's literally playing the exact same role as the derivative in this equation up here. It's what I like to call an eyebrow raiser. Whoa. I wonder if maybe the gradient vector, in some reasonable sense, I should think of as being a derivative of sorts. And in fact, that's absolutely right. We really should think of this as being a kind of a derivative of sorts. Okay, we'll say more about that later. I just kind of wanted to get you thinking about that for the moment, but we'll flesh it out when we have more ability. Okay, so back to, let's see, do like that. Back to where we were. We've got this new formula. Let's punch up a quick example. I'm going to be super quick with this example. It's very plug and chug. Again, we have this formula for linear approximations. Our goal is going to be to write a linear approximation. So in fact, all we're going to do is we're just literally going to plug in into this formula, and this is what the punchline is going to be. Some of this you can see coming really easily. We have a function, f. There's the f. We have a point A. Color. We have a point A that we want to plug into it. And if you take that A, plug into that f, the value of the function pretty easily seen to be 5. Okay, nothing to it. X minus A, again, kind of a freebie. X minus A. There you go. Keeping in mind that the x vector represents, the coordinates of your position, whatever that might be. Above, position was defined by x1, x2, x3, etc. That's why I call it the x vector. Now, to be fair, here our input vectors are called x and y. Okay, whatever. They're just variable names, right? Nothing to worry about. But the position, x comma y, is what this x vector represents. And then I subtract a. Actually, let me color code this. X vector is x comma y, and a is 1 comma 2, as previously noted. Okay. So I'm just plugging in. I haven't done, there's no tricky curves here so far. I'm literally just plugging in. Where I do have to pay a little bit of attention is first I have to figure out what is the gradient vector, and keep in mind there's our formula. It's made up of the partial derivatives. Now again, I do have to plug in A into those partial derivatives. And the punchline then is that the gradient evaluated at A, the thing that I need to dot with, is 2, 4, and that goes there. Everybody happy? Plug and chug. Okay. All right. Oh, and a quick little observation. Yes, you can dot this out. You can collect terms, blah, 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 and you can kind of streamline anyway the formula for your linear approximation. You can write it like this instead of like that. Now let's talk about pros and cons. Right? What would be the purpose of doing this? Specifically the purpose of rewriting that like so. It's a little bit simpler in a way, I guess. Why would I care about that? Well, if I were going to code this into a computer, this would probably run just a teeny tiny little bit faster, I guess. We're not going to be doing that. So, not really much of a point. What is the nature of the algebra being done here to simplify this into this? Is that algebra, like, sophisticated? Is that algebra what I'm interested in testing? No. I mean, it's I guess technically there's a dot product in it, right? But that's pretty ancient old news. On the other hand, this original version that we have has some pretty nice features by itself. The way this is written, I can eyeball glance and see what the value of the function is. I can eyeball glance and see where this linear approximation has been evaluated, and I can eyeball glance and see what the gradient is. I like that. I think it's good to be able to look at what you've written and see where it comes from and what it means. I think it's a good thing, right? So, totally honest, I don't think I would rewrite this. I think I would just leave it like this and don't bother multiplying it out. Because this is arguably kind of, whatever ways this simplified version is better are trivial, marginal, irrelevant advantages, and the ways in which this is better, I think, are a little bit more meaningful. So, anyway, for your consideration. On an exam, I will not be unhappy if you leave it like this, unless somehow the question explicitly says otherwise. Feel free to leave it like that. Okay, all right. Now, real quick, back up to here. Multivariable linear approximations. Multivariable means multiple input variables. We started with a great big clunky version, and then we rewrote it eventually as a streamlined version. Okay, that said, we're now going to entertain what happens if we have more than one output variable. Right, this is real valued for the moment. What if we have multiple output variables? So, roughly speaking, I could give you the same sort of song and dance. I could first give you the ugly version and then say, hey, oh my gosh, I recognize that expression. Let me rewrite that in a streamlined way. I'm not going to do that because, frankly, the fully fleshed out, expanded version is too big. And this little exercise of simplifying is, well, you've already seen an example of that, and it's just not that big a deal. So I am going to skip straight to the streamlined version. And here it is. If you have a multivariable vector valued function, and you want to write the linear approximation, in other words, the first order polynomial that has the same value and all of the same partials. I emphasize when I say all of the same partials, I mean all of the same partials with respect to all of the inputs and of all of the several, right? We now have M different output variables, all of those output variables with respect to all n of these input variables. And I want to find a single linear, well, first order polynomial function that mimics in that sense. And here's the formula. Notice, written very compactly, right? The thing where the gradient had been is now a matrix, and this is what that matrix is. And I'll go ahead and point out it kind of already smacks of gradient. The gradient was a vector in which I said, let's take all of our partial derivatives and kind of put it together. Here, let's take all of our partial derivatives and kind of arrange them together. This time, though, I have kind of an array because there's not only various different input variables, there's also various different output variables. So it's a pretty copycat idea, and more to the point, it works. Okay, so this is the linear approximation of a vector-valued multivariable function. Make sure to memorize this formula. It's fundamental, it's very important. You're going to be using it on a regular basis. It has these properties, as we discussed, that make this a worthwhile thing. Yeah, there you go. Let me pause real quick for questions, and I'm going to say a few more things about the DF matrix. Everybody all right?
So,
yeah.
When we are going from Rn to R1,
yeah,
we, like, the vector went from, like, the partial derivative with respect to x down to xn. But in this case, when we're moving down, we're changing the partial function. Like, we're going from f1 to fm. And then x1 is constant.
That's right. So in the previous case, when we had only a single output variable, we would effectively only have this single row. Okay. That's right. And now something I was going to point out, and this is actually a great time to do it, so I'll go ahead and do this. One could say, hey, whoa, slow down. We already had an answer for the real valued case. Now you're telling me I've got the appropriate special case of this is a seemingly different formula. Here I'm multiplying by a matrix. Here I'm dotting with a vector. So which is it? The answer is they're exactly the same, right? Because dot with a vector, keeping in mind that the elements of that vector are the partial derivatives, is exactly the same as multiplying by a row matrix. Okay? So this DF matrix, if it is a single row matrix, that is, if there is, in fact, a single output variable, then it is exactly the matrix that multiplication by which effectively does dot product with the gradient. So yeah, exactly the same answer, and it's a great question. Okay. All right. So plug into. I do want to say a couple other things about this matrix. So just kind of heads ups. We already sort of made this first observation. This is literally the gradient if there's only one output variable. But let me say that differently. If I were to just be interested in the component function f1 itself, maybe there are several other variables. But if I just want to talk about f1 itself, this is literally all the partials of f1. It is literally the gradient of f1. And likewise, all of the other rows as well. So, for example, this being all the partials of fm is, it's a, matrix, so if you want to say it's a transpose of, okay, sure, fine. In terms of its elements, it is the gradient of fm. So that's a neat observation. The columns are a different way to think about this. What can I say about this column? Well, interestingly, all of the partials in this column are all with respect to the same input variable x1. And there's a point of view on this that I don't want to get into right now. But let me just say I like to think of the columns as corresponding to input variables. Because any given column, all the partials are with respect to the same input variable. So, for example, I will think of this as the x1 column, this as the xn column, and likewise, I'll think of this as the f1 row, ... and this is the fm row. Now, the last little comment about this, I'm sure you've noticed it's very organized and orderly, how we put the appropriate partials in various places. Kind of perfectly obvious how to, you just kind of lay them out in the pattern, right? But it is easy to mess this up. You'd be surprised how easy it is to mess this up. In particular, a lot of people will accidentally transpose this matrix and have columns that they correspond to output variables instead of input variables, and vice versa. And that's extremely wrong. So, yes, it's a matrix of partials. Yes, you put them in a kind of an order, but if you transpose this matrix, you've written down something that doesn't work. And so really, really importantly wrong. So this is a little landmine situation. You want to make sure that you don't whoopsie the layout. Right? Be super careful. It's just, if you whoopsie it, then what you've written down isn't worth anything. So easy to avoid the problem, but also easy to make the problem. So be careful. Okay, so again, a little plug and chug down here. I'm going to let y'all read this one. This pretty straight read. Again, I'm just taking our general formula here and plugging in, and again, x minus a, well, there it is, and f of a, well, plug it in, there it is. Keep in mind, in this example, it's a vector valued function, and so the value of the function is a vector, as it should be. And then again, you just have to figure out what the derivative matrix is, and the derivative matrix ends up being this, because the derivative matrix is ultimately made up of a bunch of partials, into which I have to plug my point A, thus giving me that derivative matrix. So I guess I did the example after all. Anyway, but it's very quick. Now, don't trust me on the details, right? Make sure that I did all this right. Make sure you can compute this matrix correctly. Partial derivatives. Easy to do, but it's a recent thing. Make sure you can do that. Make sure you remember, so easy to forget. Make sure you remember that when you're taking partials with respect to x1, so when you're taking partials with respect to x, y is to be treated as a constant. Easy to mess that up too. And I've seen students in this top left entry write 2x plus 2y. And that's, again, nonsense. So easy to get it right, but easy to get it wrong. Okay. So I've already made these observations. The columns are partials with respect to inputs. The rows are gradients of outputs. So you can think of the DF matrix either way. One little quibble, terminology. If you look back at the name we've given to this function, we've called this the linear approximation. Unfortunately, it is in fact not linear. That's unfortunate, isn't it? It's not linear. It's not linear in the linear algebra sense. And that's just because this f of a out front, linear transformations all have the feature that when you put 0 in, you get 0 out. This messes that up. So this is not linear. So why do we call it linear? Well, because it's a degree 1 polynomial, I guess you could say, but more to the point, the part of this function that is doing the heavy lifting, the part that's really doing the approximating, most of the work of this function is this term right here, which you'll recognize is a linear transformation, matrix times vector. Right? So this is a linear relationship between the input change, x minus a, and the output change that you get by multiplying by that matrix. Okay. Okay, another little bit of terminology. Quick flashback to single variable. Y'all remember tangent lines? Tangent lines are the graph of the linear approximation. Let me remind you, this is easy to mess up. The linear approximation is a function. It's an algebraic critter. It is not a line. This part's important. Linear approximations are functions, not lines. Right? The tangent line is the graph. It's the graph of the linear approximation, not to be conflated with the linear approximation itself. So, again, fussy, sure, okay, I guess. But it's an important fussy because if you don't distinguish between a function and its graph, then you're implicitly going to find yourself assuming, very wrongly, that every picture you see is a graph. It is not. So, important distinction. Please do not, and I know in high schools and a lot of single variable calculus courses, they kind of let you get away with murder on this point, right? And if you say, hey, you point to the linear approximation and say, hey, this is the equation of the tangent line, they'll let that slide. You can't, right? It's importantly different. So if the question on a homework or an exam asks for the linear approximation, don't give me the graph of the linear approximation, and vice versa. Okay. So, all right. So that's sort of cleaning up a problem from single variable. Notice what we have down here is highly analogous. I lay it out on the page in as analogous a way as I can for sort of to emphasize the strength of the analogy. Again, we have a linear approximation. Whoops, wrong color. Again, we have a linear approximation. And again, we have a graph of that linear approximation. This ends up being the equation of a plane. This is what we call the tangent plane. And in the same way that the tangent line, we call the tangent line because it's a line that's tangent to the graph of the original function. Likewise, we call this the tangent plane because it's a plane that is tangent to the graph of the original function. Okay. All right, so same deal, same warning. Make sure to not conflate these two different things. How are we doing? Is everybody happy? All right. Okay. Makes me sad to say so, but we're not going to cover these next 2 pages. There are some really cool, mathematically very interesting, mathematically fairly non-trivial questions about differentiability. We've written down this thing called the linear approximation. Is it really? Does it do what we claim? Under what circumstances might it not do what we claim? And I'm sad to say, yeah, sometimes it really isn't, right? And I just, very quick passing reference. Take a look at this example right here. Now, I'll confess that's a strange looking function. The value of the function is 1 when either coordinate is 0, and then the value of the function is 0 everywhere else. So it's a weirdo, right? Weird looking function. But here's the thing about this function. You can totally compute the linear approximation because the function is perfectly well defined at the origin. The gradient is perfectly well defined at the origin. You could write down f of a plus gradient of f dot x minus a, write it all down. No problem at all. Everything's fine. And yet, that linear approximation, air quotes, what we have previously called a linear approximation, is a poor approximation of this function. And look how far off it is. It's way off. Right? The function's 0 almost everywhere. A couple of small handful of points where it isn't, and we're approximating 0 with 1. Terrible. Okay, so the formula we wrote down makes assumptions, and the assumptions that go into those formulas we wrote down are actually kind of subtle. And how do we flesh out exactly what those assumptions are that we need to make that linear approximation actually work and not have catastrophes like this? Long and very interesting discussion that I have to sort of confess is ultimately really not quite what this course is about. So it makes me sad. It's a super cool conversation, but we're not going to do it. FYI, we are eventually in this conversation we're not going to define something called differentiability. And part of the reason this makes me sad is that differentiability is the condition that we need to require in order for a bunch of the theorems that we're going to write down to actually be true. It's a big deal. It's a very important concept. You'll notice it's nowhere near as easy to define as it is in single variable. Right? In single variable, a function is differentiable if you can differentiate it. As simple as that. Not much of a story in single variable. It's a much more sophisticated, non-trivial story in multivariable. So anyway, that said, we are going to make one more reference to differentiability. Basically, I'm going to show you a workaround that will solve our problem. But the definition itself, I just wanted you to see it. Here it is. Yes, it's kind of creepy looking. And there's a lot to say. And okay, anyway, enough of that. Okay, I do need to make a reference to this at the bottom. You'll notice that the numerator up here is this thing called E. E is for error. It's the difference between the actual value of the function and your estimated value of the function. Error is a natural thing to call that. Okay. But when you rewrite it like so, here's a different way to think about it. You can view it as the actual change in the value of the function minus the estimated change in the value of the function. It's the exact same thing. In both cases, it's actual minus estimated. Whether you're keeping track of the values or the change in the values, that difference is the same exact thing. Simple algebra, of course. So these two objects are actually something that we're going to be referring to. So heads up, we're going to refer to the increment. Increment just means the actual amount that a function changes from one point to another. We're also going to be interested in this estimated change. This is called the differential. I know y'all have heard that term differential before. Differential is just a linear estimate of an increment. Linear estimate, that's all it is. So heads up about the term differential. And by the way, I got told some real howler nonsense, like wow nonsense when I was in like high school and stuff about what differentials are, and I got told this kind of con job about infinitesimals. Have you ever heard of infinitesimals? Okay, if you've ever heard of infinitesimals, if you are in any way attached to infinitesimals, FYI, that's all 100% nonsense. Okay? There is no such thing in the real numbers. There are no such thing in the real numbers as infinitely small real numbers. Not a thing. And if this makes you feel a little uncomfortable, come to my office hours. I will very much enjoy showing you what kind of nonsense follows from that nonsense assumption. Okay, so anyway, we have no need for infinitesimals. It's basically a nonsense idea. Differentials are much simpler than that. They're just, it's a linear estimate of how much the function changed. Okay, all right. Okay, moving along. A couple of, I got ahead of myself. Yeah, so let's straighten out this matter with differentiability. We have in this awkward position that the definition of differentiability is hard, and yet we need to be able to talk about differentiability. So what we're going to do, and what I have previously called a workaround, is we're going to talk about this thing called continuous differentiability. Continuous differentiability is a stricter condition. every continuous differentiable function is differentiable. So this is what we mean by stricter. Wow, differentiability was hard to define. You would think this stricter condition would be even harder to define. And it's not. Continuous differentiability is actually a really easy thing to define. Continuous differentiability says just that the partial derivatives exist. Nothing explodes when you compute the partial derivatives. And that the partial derivatives are continuous. That's it. Super easy. Casual glance in most cases you can confirm, yeah, that function's continuously differentiable. So this pair of observations that we have this easy definition of continuous differentiability, and we have this implication here that every such easy to define continuously differentiable function, every single one of them is also differentiable. This is the workaround. If you find yourself needing to confirm that some function is differentiable, don't do that stuff on the previous page. Oh my gosh, it's so hard. That's way too much effort. Why would you ever do that? Rare circumstances, perhaps. In the great majority of cases, if you want to show something differentiable, check that it's continuously differentiable, which is effortless, and then cite, therefore, it's differentiable. Boop. Done. Everybody on board? Okay. Which brings up the question, why wouldn't we just define this to be differentiable in the first place? Right? There's a reasonable question there. And glance into the sophisticated stuff that this course isn't about. The reason is there are some functions, not very many, there are some functions that are differentiable, but that are not continuously differentiable. So my little workaround here, sometimes it doesn't work. And the distinction, these functions that are differentiable, but not continuously different, those functions, they still work in the big theorems that we're going to be talking about coming up soon. So the ugly definition of differentiability that we have on the previous page, it's important that it be exactly what it is. Otherwise, we're leaving out important information. Okay, so anyway, it is what it is. Okay, let's see this in action. Let's see here. I can get this all on. So here's the example. Here is a function, and I want to know, is it differentiable? Now again, if you go straight at this question, if you look back at the definition of differentiability, you've got some severe ugliness to contend with, and please don't do that. Right? So we're going to do this the easy way. I'm going to first confirm that this function is wrong color. I'm going to confirm that it is continuously differentiable. So I'm going to have to think about the partials. I'm going to have to confirm they exist, and I'm going to have to confirm that they're continuous. So let's think that through. Looking at this function, what are the partial derivatives? Well, I could write them down, but they're all polynomials. All of which exist. Right? Polynomials don't ever fail to exist. Polynomials don't ever explode. Right? They're also always continuous. Old news. Right? Okay. Well, that immediately tells us then, based on this definition up here, this implies f is continuously differentiable. And once I know it's continuously differentiable, then it follows from that theorem that it's differentiable. Everybody good? Okay. Okay, so that's how, in practice, most of the time, that's how you're going to confirm a function is differentiable. You're going to confirm even more than that. You're going to confirm that it's continuously differentiable because it's easier. So take the partials. Note that they exist. Note that they're continuous. Game over. Okay. All right. Another little, again, this is a digression. It's not really what this course is about, but, oh, yeah, sorry, go ahead. Yep.
Is it like differentiable and continuous differentiable over the interval or
We're just looking, I understand the question. So the definition is 1 point at a time, right? But when we talk about a function being either continuous or differentiable or continuously differentiable on an interval, what that means is that point-defined condition is true for every point in the interval. Yeah. So both in this case, right? So this polynomial, it is, its partials are continuous at every individual point. That means that this polynomial has partials that are continuous in general over the interval. Yeah. Yep. All right. Okay, so this next thing is, it comes up every now and then. Turns out, not hard to show, actually, that every differentiable function is continuous. Now I'm going to pull a move called the contrapositive. This is a slick move. This should be in your toolbox for sure. If P implies Q, then not Q implies not P. Do y'all know this one? Have y'all heard this one before? Very, very useful. It's a way of taking a statement and kind of turning it upside down and backwards and getting another known true statement. And there's all sorts of sort of, fun examples of, how, basically clear this should be. So anyway, that's all I did here, and the second version down here is the one that's actually useful. If I want to address the question of differentiability, all I have to do, in some cases, if I can confirm the function is not continuous, then I immediately know that it is not differentiable. And I don't have to entertain the differentiability question. I already know it's not differentiable. It's not even continuous. Okay. All right, and here's an example. It's the example that we saw a couple pages back. Okay. All right. Okay. Now this next couple of pages is really just interpretation. There's not really anything particularly new on this next page. It's just sort of a way to think about what we've already defined. So here's our linear approximation formula. Vector valued, multivariable linear approximation. And keep in mind, one of the requirements is that f has to have the same value as L at the point A. And then, note, it's actually really easy to take this and kind of whip it around over here to the other side of the equation by subtraction. And so, we're a hop, skip, and a jump away from the linear approximation being this formula. And this formula we can interpret actually really, really nicely. So this formula says that how much I change in the input, now this is literally the difference between the point where I'm doing the approximation A and the point where I'm evaluating the approximation x comma y r. This is what you might say then is how much I move, how much my input changes in the domain. It's what we call the input differential. And then notice the output. It's not the increment. It's not how much f changes. It's how much L changes. Namely, it's the change in our linear approximation. Or you might say It's our linear estimate of the change of f. And you remember we defined that as the output differential. So changing the notations accordingly, effectively the linear approximation turns into a thing that I can rewrite as this. And said differently, this matrix, df, this is the thing that gives a relationship between input differentials and output differentials. This is the thing that relates input changes to output changes. Approximated, of course. And what do we call the thing that relates input changes to output changes? You may recall that's the very first thing I said about derivatives. That's fundamentally what a derivative is. In any context, in any case, some way or another, a derivative is a relationship between input changes and output changes. 2 seconds. And so, as you might expect, because this turns input changes into output changes, we call it the derivative. And that feels weird to call it the derivative. Hey, wait a minute. I thought derivatives were numbers like slopes. Not anymore, they're not. It's one of the weird things you have to get used to in multivariable calculus. Derivatives, in general, are matrices going forward. And this df matrix, that's why we use the D. The D is for derivative. Yes, I'm sorry.
So when we were calculating partial derivatives for I think yesterday for the literal picture.
Yeah.
We got a similar like this. So
Totally.
Is that?
It's just a different. I would say it's just a different interpretation. I mean, we took this unnatural. Okay, let me rewind a little bit. I'm going to propose that df is a very natural thing. Right? All we assume in order to talk about df is that the function's differentiable. And then this is a relation between input changes and output changes, and it does its job, and so it's the derivative. Partial derivatives, let me just let's look back on it. Now that we're in a better place, let's kind of chastise ourselves for how silly we were back then. We very first thing said, I don't like the function we have. It has too many variables. Let me play make-believe and pretend that they're constants. So we kind of made up some, I'm going to call it a little bit of nonsense, just a little bit. Right? And so I'm going to rephrase your question just a little bit as, hey, how does this thing that makes sense relate to that nonsense we did a couple of days ago? Well, okay, they're kind of related in a way, right? And that's why you noticed, right? But the difference is a consequence of partial derivatives basically being just a little bit nonsense. Does that satisfy? Yeah. Yeah. So this is the more general idea of a derivative, and again, when you leave this class, you remember how I was saying. In fact, let me actually go back a few pages here because I think this is important. Yeah. Derivatives and multivariable calculus all have this feature. They relate input changes to output changes, right? So that's what we were just talking about. And partial derivatives, I gave you this warning. This is not how you should think about multivariable derivatives. I made the observation, we're going to have something much better than this. And that thing that is much better is what we just saw. DF. The DF matrix is that thing that's much better. So when you leave this class, let me say this differently. 20 years from now, when y'all have faint memories of multivariable calculus, that the derivative is a matrix is on my top 5 list of most important things that, my wish list of what can I, if I could only have 5 things to ensure that you remember in 20 years. Be one of them. Yeah.
So just to clarify, but in this case, the derivative is like an approximation.
Well, the derivative, so the derivative is an exact thing. It is exactly what it is. What it does is make an approximation of how much the function changes. Yeah, it's just like if you think about it, that's what a single variable derivative is, right? If I compute a derivative and I find the value of the derivative of a certain function at a certain point is 3, well, that's exact. But if I then use that derivative to estimate the value of the function, just a little bit nearby, okay, that's an approximation. Is that cool? Yeah. Okay, so totally analogous here. Okay, just a little bit more terminology. Because it's a matrix, sometimes this gets called the derivative matrix. No surprise there. Because matrices are linear transformations, sometimes this is called the derivative transformation. That one's a little bit less sort of expected, but if you think it through, it makes sense. Right? And that's what matrices are, ultimately, linear transformations. So derivative transformation makes sense too. So you'll hear that when you hear derivative transformation, you just got to remember we're still talking about the derivative matrix, aka the derivative. And I think that's the one that's going to catch you off guard the most, is that when people say the derivative, again, you're going to kind of reflexively think of that as being a number. And you got to remind yourself, no, not anymore. Derivatives are now matrices, at least in general. Yeah.
So the df, it's still like the matrix of
partials.
partial derivatives.
Yep, absolutely. Yeah, and so let me comment on that. So, yeah, it's this weird thing where I just got, her question over there. I was making fun of partial derivatives as having been this kind of laughable idea that, silly us, going around making assumptions and stuff like that, right? Right. But, per your point, yeah, that silly nonsense is how I actually compute this much more legitimate thing. So yeah, partial derivatives are extremely useful. We need partial derivatives because they help us compute important objects. That's the way I would say, yeah.
Another question is, how can I geometrically interpret?
Yeah, that's coming up. Okay. Yep, totally. Great, exactly the right next question, yeah. Okay, one other thing I want to say about terminology and notation. Sometimes the D is written as a J. And that's because another name for the derivative, aka the derivative matrix, aka the derivative transformation, another name it's called the Jacobian matrix, after a mathematician. And JF is suggestive of the Jacobian. So, I'm going to use D's and call it the derivative matrix, but the multi-course that I took when I was y'all's age called it the Jacobian. I anticipate I will probably at some point reflexively fall back to old, habits and call it the Jacobian. So anyway, if that happens, that's what it is. Okay, what do these things look like geometrically? I'm going to just take this equation right here and keep in mind that, DF, it's the thing that turns input changes into output changes. And let's actually just kind of write that down. And here it is. If you have a function that takes, let's say, that point A to this point f of A, so f takes A to f of A, point to point. The derivative matrix, again, takes input changes and turns them into output changes. Well, an input change would say this input point A, from there, I'm going to displace by some amount. This is what we mean by an input change, an input differential. And there would be a new value of the function that would be, let's see, I'll put it about right there, I guess, maybe, I don't know. So, when you move in the domain, there will be some, in fact, I'll even do this. So this new point right there, that new orange input will have some orange output. If you want to estimate the change, keeping in mind your estimates are never quite right. Right? They're always off a little bit. That's why we call them estimates. So the derivative matrix aka the derivative, is the thing that turns that input vector, that input change, into this output change. So again, it's not perfect, but the big idea is that when you're doing linear estimates, the linear estimate of the change is what you add to the original value to get your best estimate that you reasonably can in a linear sense of what that new output value is. Everybody good? Just like in single variable calculus, by the way. Okay. So this is somebody I already forgot who asked, but how do you think geometrically about the derivative matrix? And this is how I like to think about it. It's a linear transformation that turns. By the way, what do linear transformations do? They turn input vectors into output vectors. That's their job, right? Well, that's what df does. When the input vector represents a change to the input to the function, and the output vector represents the resulting differential, aka linear estimate of change of the output of the function. Yeah.
So would you call this a literal picture?
Oh, well, yeah, sure. I drew it, so yeah, it's kind of a picture. Yeah, absolutely. Now, what I'm drawing, so a reasonable question then, is this a graph? Nope. Is it a level set? Nope. Is it, you can go down our list. It's kind of a new picture. This is arguably a picture of a derivative matrix thought of as a function, and I'm viewing the inputs not as points, but as displacement vectors. And I'm viewing the output not as points, but as output differential vectors. Yeah, absolutely. All right. Okay, similarly, this original formula we were just looking at, right? Input differential, output differential, the derivative matrix is what relates input to output. Divide both sides by dt. I mean, I'm being a little floppy here, but I'm going to say morally this is fine. Formalities, awkward. But morally this is fine. And so that gives us what I'm going to call a new interpretation of the derivative matrix. Now the derivative matrix relates, relates this, whatever that is, to this, whatever that is. And I'm going to make a case coming up in just a moment here. But for the moment, I'm going to appeal to your kind of flashback memories of how to interpret derivatives back in Calc 1. The derivative of position is velocity. And so I'm going to think of this then as the input velocity. So in particular, if from that point A, if instead of making a discrete jump from here to some nearby point, if instead I just say, look, I'm at the point A, and at this exact instant, I'm moving with a velocity in the domain, then the derivative will multiply by that input velocity to give me the velocity of the output point in the target. So you can think of the derivative as a relationship between discrete changes. Just for cleanup purposes, let me do that. You can think of the derivative as a relationship between discrete changes, or you can think of it as a relationship between instantaneous rates of change. So, By the way, notice that in each case, whether you're interpreting the input vector as being a discrete change or a velocity as a rate of change, in either case it's represented by a vector, right? And so you can kind of generalize both of these ideas as the derivative relates input vectors to output vectors. That's a reasonable take. Okay. And just to flesh out there we go. Everybody happy? Good deal. Okay, moving along. I've already made this observation, so I'm going to be quick with it. Somebody asked a great question earlier that got me onto this little digression. But, you could play the same game that we just did up here. Let me just refer back to it, right, where you take the linear approximation and you just kind of rewrite it as a relationship between input changes and output changes. You can do the morally equivalent algebra, the exact same thing, for the real valued case, where you have dot product with the gradient. And you get, unsurprisingly, pretty much the same thing. And so I'm going to go back and ask sort of, same question. What's the difference between dotting with the gradient? Here, let me do it like this. Dotting with the gradient versus matrix multiplication by a row matrix. And again, it's the exact same thing. The gradient is a column vector consisting of all the partials. df, in the real value case, is a row consisting of all the partials. It's all the same stuff, just kind of assembled in a different, a slightly different way. And so these two computations here, whether you are multiplying by a derivative row matrix or whether you are dotting with a derivative column vector, it's the same arithmetic. It's the same. It's just ultimately different notation for the exact same stuff. Okay, so take your pick. You can think of it either way, and choosing momentarily to take this gradient point of view. Well, input differential. When I dot with the gradient vector, that turns that into the output differential. And just do keep in mind this output differential, because we're talking about a real valued function in this case, that output differential is now a vector on the real number line. So it represents either a change in that single real value or the velocity of that single real value. Okay, same idea, different notation. All right, everybody good? Okay, couple things we have to say about higher order derivatives. Flashbacks to Calc 1. You spend time in Calc 1 talking about the derivative and interpreting the properties, and then someone comes along and says, what if you take a derivative of that derivative? Things get a little weird, and you have to interpret, how do I interpret a derivative of a derivative? And you got to think it through, right? And what you come up with is this idea of concavity, right? So you have a geometric interpretation of a second derivative. Again, all Calc 1. Okay, so a higher order partial is going to be basically that same idea. If you have some multivariable function, you talk about a partial derivative, you can then ask, hey, what would happen if I took a partial derivative of that? Okay, we're going to talk about geometric interpretations of higher order partials momentarily. Real quick, I do want to remind you, though, that the act of differentiation is linear. Ultimately, this is all that means. Hopefully this formula is, vaguely familiar. Not as it's written, of course. But suggestive of something that hopefully is very familiar. Namely, if you have a combination of functions and you want to take the derivative of think back to Calc 1. If you want to take a derivative of a combination of functions, you take the derivatives of the individual functions and just kind of the constants and the plus just kind of stick around for the ride. Right? Y'all done this a million times when you do stuff like the following. If you want to take the derivative of 3x squared plus 2e to the x, right? Well, there's different ways you can write this down, but probably an easy sort of first step would be to say, well, yeah, just take the derivative of the x squared and take the derivative of the e to the x. And then, don't forget the 3, and don't forget the plus, and don't forget the 2. So y'all have done stuff like this a million times. Well, all this is the same. And it is a sort of a linearity. It's a sort of a linearity in the sense that here we have a linear combination going in to the differentiation, and here we have a linear combination of what comes out of the differentiation. That's what linearity is. So that's all that is. Whoops. Okay, close enough. Then there's an example. I do think this is a healthy exercise to take a look at. Please do take a look. I think this is very readable. And notice, as expected, the derivative of a combination, right, is the combination of the individual derivatives, just like the formula above says it's supposed to be. So think it through, work it out. Take a few minutes to do that. Also note that in the book there's a few formulas. I'm not going to spend class time on these formulas because it's just plug and chug. It's also kind of exactly what you would sort of expect. So nevertheless, look at them. There are some conditions. The Legos have to fit together. You can't write down nonsense, right? But that said, there's kind of a product rule and a quotient rule in many cases, and so make sure to look that up in the book, and then notice that you can confirm those formulas by literally plug and chug. It's no big deal to confirm those formulas work. Okay. All right, so let's talk about higher order partials. As we discussed, if you have a function and you take the partials of it, like so. By the way, quick reminder, we've talked about this notation. I got too much on the page here. We talked about this notation, the subscript notation. It's kind of Newton-like notation. And we've talked about this notation. This is what you might call Leibniz-like notation. Of course, you can do the x partial or the y partial to whatever function, such as this one, and you get a couple of different partials. Okay, fine. Where it gets interesting is this x partial. You could talk about the x partial of that, and that's called, unsurprisingly, the x second partial. And the notation, there it is. It's a little unfortunate. I've always been a little uncomfortable with this, but it's just notation, and I'm going to say, let it go. Yes, it's annoying. Yes, it's a little bit, not quite right, but it is what it is. So we're not actually squaring. I'm not multiplying partial times partial, right? It's just that we have a partial of a partial, and there's two of these symbols right next to each other, and it's just streamlined, right, partial squared. It's just notation. And likewise, this partial x squared. And this one bugs me because it looks like partial with respect to x squared. It's not. Again, just notation. Okay. And then likewise, I could take the y partial of that x partial. Right? You start with an x partial, then you can take the y partial of that. And again, let's talk about the notation. How would you write that down? Let's see here. How am I gonna? Okay, right. So we start with an x partial. You can take that x partial and write it like so, or you can write it like so. Here, let me do it like this. So you can write the x partial in either of those ways. And then the act of taking the y partial of that, you can write either like so or like so. And I will call your attention to the fact that this is also awkward. The Leibniz-like notation is sort of, if you will, on the left of the function. The Newton-like notation is, if you will, kind of on the right of the function. And so when you take the y partial of the x partial, these two notations seem to have the y and the x on opposite sides of each other. And it makes it look, I mean, if you're not careful about it, you might think that these are different from each other. They're not. They're just, that's the unavoidable consequence of the notation being like this. Is that acceptable? Let me rephrase that. I hope that's acceptable. Better be. This is what we're up against. This is the awkward notation we have to deal with. So be it. So yeah, so heads up. When you're using the Leibniz notation, the second one is on the left. The first one is on the right. When you're using the Newton notation, the first one is on the left, and the second one is on the right. So, oh my God. So, anyway, there you go. Okay. By the way, neat fact, and I multiplied this out for one of them, but so here you see I took the y partial of the x partial. Here I took the x partial of the y partial, and OMG, look at that, they're the same. What are the odds? Whoa, weird. Is that a coincidence? Will we always get lucky like this? And the answer is definitely not a coincidence. We technically won't always get so lucky, but surprisingly often we will. And so now what I've written down here is just kind of, I wanted to write this in a way that's actually kind of precise. The book does too. But all this is saying, look, if you got some function f, and if you're going to take various partials, and you want to talk about, yeah, well, what if I do those partials in different orders? All the same partials, just I want to do them in different orders, maybe y before x or x before y. Then it's all good. That will work if a certain condition is satisfied, and the condition is the function has to be what we call CK. So the partial derivatives have to exist and be continuous, and not just the first partials. However many grand total partials you want to talk about, that's how many we have to know exist and are continuous. That's what's called being a CK function. And the good news is there are broad categories of functions that are obviously not only CK, but C infinity. So for example, polynomials. You can take all the derivatives you want of polynomials. You can take derivatives of those derivatives and derivatives of the derivatives of the derivatives. Keep taking derivatives all you want. If they're polynomials, you're always going to get other polynomials until eventually you get zero. And that you can, of course, take as many derivatives as you want. So, for example, then, for polynomials, no problem. Exponentials, blah, blah, blah. Okay. All right, what do these look like? Let's see here. Wait a second. I guess I am out of time. Okay, I'll tell you what. We're already at the end of a page, so this is a pretty good place to draw the line. We will pick up here on tomorrow. See y'all later. Have a good one.